In this module, you will learn to prove mathematical statements by applying the principles of mathematical induction. Let's recall the basic principle of mathematical induction. Consider a mathematical statement P of n involving natural number n such that the statement is true for n equal to 1, or in other words, P of 1 is true. If the statement is true for n equal to k, where k is a positive integer, then the statement is true for n equal to k plus 1. In other words, if P of k is true, then P of k plus 1 is also true. Then, P of n is true for all natural numbers. Principle 1 is a statement of fact, while Principle 2 is a condition. If P of n is true for all n greater than or equal to 2, then the first step starts from n equal to 2, and we verify the result of P of 2. Next, if the second principle is true for n equal to k, then it is also true for n equal to k plus 1. Let's apply the principles to the following statements. Let's begin with the first statement. Let the given statement be P of n. Let's check the truth of the statement for n equal to 1. For n equal to 1, both sides of the statement are equal. Therefore, P of 1 is true. Let's assume that P of n is true for some natural number k. On replacing n equal to k, we get this statement. Let this be equation 1. Now, we have to prove P of k plus 1 is also true. Let's add the next term of the series to both sides of the statement. On factorizing the numerator, we get 2k plus 1 multiplied by k plus 1. The denominator can also be written as 2 times k plus 1 plus 1. This is equal to P of k plus 1. Therefore, P of k plus 1 is true. Hence, the given statement is true for all natural numbers n. The second statement is 2 raised to the power 3n minus 1 is divisible by 7. We have to prove that the expression is divisible by 7 for all natural numbers n. Let this statement be P of n. First, consider the value of n as 1. On replacing n with 1 in the statement, we get 7, which is divisible by 7. Therefore, P of 1 is true. Let the statement P of n be true for some k belongs to n. Therefore, 2 raised to the power 3k minus 1 is divisible by 7. Let this be equation 1. Now, we have to prove that P of k plus 1 is also true. On replacing n with k plus 1, we get 2 raised to the power 3 times k plus 1 minus 1. On simplification, we get 2 raised to the power 3k multiplied by 8 minus 1. We'll write 8 as 7 plus 1. On simplifying, we get 2 raised to the power 3k multiplied by 7 plus 2 raised to the power 3k minus 1. 2 raised to the power 3k multiplied by 7 is a multiple of 7. And 2 raised to the power 3k minus 1 is divisible by 7 from equation 1. Therefore, the statement is true for n equal to k plus 1. Hence, the statement is divisible by 7 for all natural numbers n.